So we're going to look now at Suds Design, and before we get into using InfoDrainage, I think it's useful to look at Suds Design philosophy. So those of you who have completed the previous sections will know that our network looks something like this. So we've got a pipe that comes down here, slopes down towards the outfall down here. We've got a pond that we've designed, and then we've got a limit of outflow which has been set to 16.1 litres a second. We can't exceed that. And then we've got a couple of additional branches, sort of one coming in here and one coming down here. And what we're going to do is to place some Suds features around the catchment and control the flow using those. And then the intention is to reduce the size of the pond at the outfall. So the first thing would be the placement of the Suds features. There is an option within InfoDrainage called deluge analysis, which is useful in determining where low spots are and where water may naturally accumulate, and that would be obviously good places to put our storage structures. But one way or another, we're going to have to derive where our storage structures are. And then this example, we're going to place a swale roughly here, and then we're going to place a permeable pavement sort of up here. Now once we've done that, each one of these structures will have some sort of flow limitation device coming out of it. And what we've got to do is determine a combination of storage and flow limitation. We've got to optimize that such that we reduce the flows coming down to the pond. We've still got the same flow limitation coming out of the pond, but the pond should be smaller because essentially we're storing water further upstream up here. Now this presents a problem in that there's a lot of unknowns here. We've got unknown storage sizes and we've got unknown pass forward rates. And this is largely my personal opinion. I've heard other people within the industry adopt a similar philosophy, but I think what you need to do is fix on one thing or another. You either need to fix the pass forward rate and then design the storage upstream of that to meet that pass forward rate, or you go in with knowing what your storage is going to be and you derive your pass forward rate such that you utilize all the storage that you have available. Now in this example, we're going to assume that the storage volumes are fixed. We only have a certain area and a certain depth, therefore a certain volume for storage at each of these locations. Therefore we can't change the volumes, but we can change the pass forward rates to optimize that storage, make sure it's just full but not more than full during our design storms. Therefore reduce the pass forward rate as much as possible so that we're passing as a lower flow rate as possible down to the pond, and therefore we can then reduce the size of the pond, hopefully without exceeding the 16.1 litres a second ultimate pass forward rate to our discharge point down at the bottom. So that's what we're trying to achieve, and the following exercise is how we go about that. So I'm going to switch back to InfoDrainage now. This is the starting point from the previous exercise. So this is the pond design file. We've just designed this pond, and as I say, the idea is to introduce some Suds features and then hopefully reduce the size of that pond. So looking back at the notes now, the first thing we're going to do is to save this file as one called Suds Design. Save that, and then we're going to introduce an additional phase. So take the pond design and duplicate that phase. Now we're going to switch off the original pond design and make sure that we don't analyze it. So we're purely working on this one, and we're going to rename that one and call it Suds Design. Okay, now just as we did with the pond, I want to bring in some background images so that everybody gets the same answer and so that we're always digitizing in the same place. So this is just a picture. We're not importing any information, we're just using it as an outline. But if we come down to the CAD information that we had before from the tree view, we've already got the pond outline there, so although it exists within the model, it's not switched on at the moment, and we're going to import some other CAD files. So this is going to be from the data directory. This time we're going to bring in those Suds outlines. DWG file, CAD base package, and this time we have lots of different layers within this file, all creating or all including a lot of different information. A lot of them is just label information, so not relevant to us. So we're going to deselect everything apart from the stormwater control outlines, and we can see we've got two there. So finish that and it brings them in. Okay, so we've got a swale there and a permeable pavement there. If you haven't already switched off the inflows, then switch them off now. We want to keep things as clean as possible. And then we're going to start to design the swale. So we can zoom in on this area here. As usual, we're going to make sure that the snap is switched on, if it may be already. And the idea is that currently water flows from manhole S9 through to manhole S10 via a pipe, and instead of that we're going to have it flowing via the swale. So the first thing to do is to highlight that pipe and simply delete it, so it's gone there. Okay, so we're going to put in our Suds features. It's very similar method as we used with the pond. We look for the relevant stormwater control that we're going to use, and there's two that's very similar, the swale and the dry swale. So in this example it's going to be the swale that we're going to be using. So take it, and as we did before, the convention is to drag it somewhere in the vicinity of where you're going to place it, and you can see the mouse pointer turns into the digitization tool, so it's ready to digitize the outline of the swale. Now previously, with previous structures, I've talked about how it's not really important how you digitize these things. You can start where you like, you can move in a clockwise or anti-clockwise direction, which is what we did for the pond. It doesn't matter how you digitize it as long as you end up with the correct boundary. Swales are different. With a swale it does matter in which order you digitize it, because we need to know which dimensions are the length and which dimensions are the width. So the way it works, and it's there in your notes, is that you start from the upstream end, so either of the two upstream points here, snap to one of them, snap to one of the corners, then snap to the other upstream corner, and then as you digitize you'll see it actually creates a rectangle. So it's not a free-form digitizing, it's looking to digitize a rectangle. So come down to the bottom point, click, and then it's created the swale like that. Okay, and as always, then go immediately back to the select tool. So we've got the swale there. Now what we're going to do is click on it, double click on it, and it's going to bring up its properties. So we should see the exceedance level is, in this case, 35.998, 36 meters. Now that's being generated again from the background surface information, although it's not visible at the moment, it is still being used in the background. So it's picked the smallest or the lowest of those 4 points and used that to derive the exceedance level. We're then going to manually define what the base level is. So grey out the depth and type in a base level of 35 meters. So this thing's going to be 1 meter deep. It's 6.8 meters is the top width, and the side slope is going to be 1 in 1. Now that may not be realistic. Although this thing is only 1 meter deep, perhaps in reality you'd have a more shallow slope than that. But through a combination of the size available, the area available, we decided that that's what's needed. Now this time it does have a length, which is already calculated based on our digitized values. We need to put in a longitudinal slope, and for the first time as well we need to put in a Manning's roughness value, because what's different between a swale and a pond is that water does actually flow along the length of the swale, so parameters like length and roughness are now important in determining the flow characteristics. So we need to put those in as well. Okay, so I think we've got now all the all the basic dimensions that we need. But one crucial difference between sud structures, swales and the like, in comparison with ponds, is that they infiltrate out of the structure and into the surrounding soil. So we hope that because we can have some infiltration from these structures, it will reduce the size and ultimately the amount of flow that's passed forward downstream. So in this case, we are going to use both a base and a side infiltration. Just going back to my whiteboard a second. So we've got the cross section of the swale there. So we're going to have infiltration both out of the base and out of the side. So as the swale fills up, so as we have a water level here, it would expose more of the side and hence more of the infiltration to the swale, like that. Okay. So our infiltration rate is going to be 0.02 meters per hour, and that's then multiplied by the meters squared of the wetted area, and then we end up with meters cubed per hour or liters per second for the swale. We've got this safety factor as well. Safety factor just divides that value by the safety factor. So in effect, we've got 0.01 meters per hour coming out of both the base and the side. Okay, so we've got our basic swale characteristics in there. The next job, just like we did with the tank, with the pond, is to connect it up, and we're going to use a very similar method than we did with the pond. So look to the connections again, and I think I mentioned as we were doing the pond, perhaps in reality it would be more realistic to connect these things up with pipes, but we've learnt about connections and pipes and how to put in invert levels and diameters, and I just wanted to make the creation of these connections as simple as possible. I didn't want to spend too much time putting in the dimensions, so I'm using a no delay purely for just speed of creation, and also no delay is useful during an outline design. Maybe we haven't got to the detailed design stage yet, we don't know exactly the dimensions of these connecting pipes. We simply know that whatever water arrives at manhole S9 will be transferred into the swale, and whatever water leaves the swale will be transferred to manhole S10. So that's what that no delay connection does. It's just saying these two things are connected and we're not worried about the dimensions of how they're connected. Okay, so take the no delay, connect it to left click on manhole 9 and then release it and connect it somewhere in the swale, and similarly as you move downstream somewhere inside the swale and then connect to manhole S10. And when you do that, if you kind of hover over it, you'll see it moves from new to inlet. Let's go for the inlet option. So click on that and it should create that. Now what we've got to do is to put what structure is going to discharge from manhole S9. So again, back to the select tool, click on manhole S9, and the outlet from this, you can see by default it's put an orifice in there, and it's derived the size of that the invert level of that orifice, and all we've got to do is put in the diameter. So we're going to use 0.03 meters. Just made that bigger than or as big as the incoming pipe, such that the orifice itself doesn't provide any restriction to the flow. What we don't want happening is we don't want flooding in manhole S9. We just want all the water that arrives at S9 to be able to make it into the swale. So the orifice needs to be at least as big as the pipe that's discharging into it. Okay, so the inlet is fairly straightforward. We just want all the water to come into the swale. The outlet is much more complicated, or there's more design considerations with the outlet, because like I said in the introduction, the idea is to set the size of this orifice such that we utilize all the storage in the swale, but obviously we don't want the swale to flood. So one of the ways of doing that is we want to work out roughly what the area is upstream of that. so we can set this discharge rate. So I hope this will become clear in a second, but what I'm going to do is create a flow path coming all the way from S1 down to manhole S9, and then under, I think it's under results, and then inflow summary, we can see that the total area upstream of this is 0.654 hectares. Now you may remember earlier we did the quick storage estimate to work out how big the pond needed to be. So we're going to go through a similar process here. So under preliminary sizing, we want to go into the quick storage estimate. Now one thing I should have shown you, I'll just come out of this a second, is if we go back into the swale, we've got an area, you can just see it down here in the bottom right hand corner of this dialog. We've got an area, a volume here of 184 meters cubed. So in other words, what we've got is we've got 0.654 hectares draining down here. It's going to go through this storage of 184 meters cubed, and it's going to discharge out of it. And we've got to set the characteristics of the discharge orifice such that we utilize roughly 184 meters cubed of storage. Okay, so we did a similar exercise previously when we were designing the pond, but this time we're working in a slightly different way. With the pond, we knew the discharge rate and we were working out the volume of the pond. Here we know the volume and we're sort of working backwards to calculate the discharge rate. Okay, so we go into under preliminary sizing, we go into the quick storage estimate, and we're going to define this time a user input, and the area is going to be that area upstream of the swale, 0.654 hectares. We're going to go with a volumetric runoff coefficient appropriate for the winter. During the winter, we're saying that of all the rainfall that lands on the roads and the roofs, 84% of that will make it into our sewage network. So of all the rainfall landing on this area, 84% of it will get into the network. Now we don't know the discharge rate, but we're going to guess that. First guess, this is just a guess, I'm going to guess 6 litres a second. The infiltration rate is those that we just applied to the swale, 0.02. Same safety factor. We've got a quick storage estimate, and we're going to use the same set of storms that we did before. So you hit calculate with that, and it's telling us that with infiltration, the volume required is going to be somewhere between 128 and 217 meters cubed. Okay, so that seems certainly in the ballpark. We can see that 184 is somewhere fairly much in the middle of those two numbers. So 6 litres a second is a pretty good guess. But what we may have to do, if that wasn't a good guess, we would go back to the input, we would change our discharge rate, and then recheck the results. And what you're looking for, like I say, is that you know the volume, you're looking for it to be midway between the quick storage estimate values. Okay, so we've got that. So we now go back to the orifice, the discharge orifice. We know the invert level, that's 35, the base of the orifice. Go into the calculator. The design depth is going to be 1 meter. The design flow is going to be the 6 litres a second that we worked out, and you can see it gives us an orifice diameter of 0.053 meters, 53 mil, which in reality is pretty small, prone to blockage. So in reality, we'd either have to design against that blockage, put in some cage or something to protect it, or use another flow control device, such as a hydro brake or something like that. But anyway, that's how we got there. That's how we derived an orifice of 53 millimeters in diameter. So press OK on that. This is a good opportunity to save the model, save our Suds Design model. And as well, let's see if we've got everything in correctly. So we're going to make sure the analysis criteria is set up. Yep, we've got the 18 storms there. So at this stage we can validate the model and we can see that there's no errors. So in other words, all our orifices, all our dimensions have been put in correctly, dimensions of the swale, etc. So good opportunity to save. Okay, so that was the swale. So let's go through a similar process with our cellular storage structure, which is going to be our other storage device. Similar process. We did expect manhole S21 to drain via a pipe to manhole S22, so we're going to delete that pipe and replace it with the cellular storage. So looking back to our stormwater controls this time, we're now going to take the cellular storage and we're going to drag it into the middle there, and you'll see it's asking you for a digitization. Now this is very similar to the swale. So what we see is we digitize 0.1, 0.2, and then we drag, and it's trying to create a rectangle. So for now we just have to go with it, just place it anywhere like that. But going back to the select tool as always, what we then need to do is to right click on that and replace outline with a free form, and that's the only way that we can get the strange unusual shape that we've got for this structure. So now it doesn't really matter the direction or where we start, we just go around and snap to the points and then right click to close. Okay, and it's draw a line from the furthest 2 points apart here. Okay, now what we do is double click on the storage to bring up its parameters. Now cellular storage I think is unique in that the parameters that we type in here do not necessarily correspond to the area that we've digitized. Certainly with the pond, you may remember that the area came from the digitized boundary, and also with the swale, parameters like length and width also came from the digitized value. But cellular storage is unusual because you buy them as crates, you know, as predefined shapes, so you don't get much flexibility. You know, you don't want to be cutting these crates in half or anything like that. So they have to be a whole number of crates. So for cellular storage only, we are defining the number of crates, and there is not necessarily a link between that and the shape that we've digitized. So be aware of that when we start typing in number of crates. In reality, this is the only structure for which you must check that the graphical representation, the digitized boundary that we've put in, matches the number of crates that we specify. It's the only structure where the size parameters are not derived from the digitization that we do. Okay, it does define the exceedance level, just as always. It picks the lowest of any of the points that we've digitized, so it should be 34.85 or 848. We're also going to type in a base level, and in this case it's going to be 33.10. Now we went through this in detail when we designed the pond. I'm not going through it in as much detail here, but your base level is going to be no lower than the pipe coming out of here. So prior to this training, I looked at the upstream invert level of this pipe, and I've set the base level of the storage accordingly. And in this example, we've got 15 crates long, 15 crates wide, and 1 crate high. Porosity, the great thing about the cellular storage is it does have high porosity, so we're only losing 5% of it through the structure of the crates themselves. And each crate is going to be 1 meter long, 1 meter wide, and 1 meter high. So you can see the overall volume is going to be 247, so 15 times 15 times 1 times 1 times 1 times 0.95 is how we derive that number there. But there is no guarantee that that area, 15 meters by 15 meters, matches the digitization boundary that we put in. You need to check that manually. As I say, that limitation only applies to cellular storage. It looks like it's lost my base level there. I need to type that in again. So 33.1. That now looks much more sensible like that. So we can see crates exist under the ground, and then there's some earth on top of them that doesn't provide any storage until we get up to the cover level there. Okay. So same effect as we had with the, or same process as we had with the swale. The next task is to connect it up, and as I said, I'll say it again, in reality we would put some effort into understanding the pipe size, its invert levels as it came in and went out. For this analysis we've looked at pipes and invert levels before, so I'm just going to connect it up excuse me, as simply as possible. So under the connections, we're just going to use a no delay to take manhole S21 somewhere into the boundary of the cellular storage, and then at the outflow somewhere within the cellular storage to, again, this new or inlet, and we're going to try and specify inlet. Just a very quick word on what that means, the difference between inlet and new. If we look at the manhole itself, what we've got is we can look at all the various ways that water can get into this inlet, and the assumption is that there's already a flow from any inflow areas which are connected to it. So water can get from the surface down through the grating into the manhole itself. And what we're essentially being asked by that new or inlet issue was, do you want the, whatever you're connecting, in this case an orifice and a no delay connection, do you want to come in via the same connection, or do you want two separate inputs to this manhole? Well, we only need one. We're not that concerned about the various different ways that water gets to this manhole. We just need to know that water is arriving at this manhole. So in the majority of cases, you can use the same inlet for the various different points that come in. For example, if we had two or more pipes arriving at this manhole, let's have a quick look at how that's dealt with. So if we look at a junction here, if we click on that and look at the inlets, you can see that in this case, again, there is just one inlet coming in, and we've got three different items coming into it. That would be the two pipes and the inflow area draining through the top of the manhole. So they all are essentially amalgamated together. We're not looking at separate characteristics, separate restrictions. They all just arrive at that manhole. So that's how it works. All of our flow restrictions are generally done in the orifices or the pipes. They're not done as water enters or exits the manhole. Okay, so just like we did before, we're not going to concentrate too much on what comes in. We just need to know that there's no restriction as the water comes in. So looking at manhole S21, the outlet from that needs to be an orifice, and that orifice diameter is going to be 0.525. Okay, and we've got the invert level set there. And again, we've got to go through the same task to work out what the limit of discharge is going to be from this structure. So just as we did before, we're going to create another flow path from some point high up in the catchment, manhole S23 I think it is, down to manhole S22, and then if we go to the results, we can look at the inflow summary, and we should see that there's 0.764 hectares coming from that. So if we go back to the select tool, just to check, so we've got 214.5 meters cubed of storage here in these 15 crates times the 0.95 porosity. So again, what we're trying to do is, we know the area now, we know the volume, we're trying to set the discharge limit such that that storage is utilized. So I won't walk you through the quick storage estimate. We've done that already. What it came out at was 9 litres a second. So all we need to do is to calculate an orifice that's going to let 9 litres a second through. So if we go into the outlets from the cellular storage again, go into the calculation, the design depth is going to be 1 meter, and the design flow is going to be 9 litres a second. And as I say, I've skipped the bit where I went through the quick storage estimate to find that 9 litres a second. But it comes out as an orifice of 0.06666 mil in diameter. Okay, so that should now be it all connected up. And again, our task is to save the model and then to validate it. And we should see that there's no errors. Okay, so we've got all the parameters that we need. Okay, so we should now be ready to go with our analysis. We've got our originally sized pond and we've got 2 substructures. So it does validate. We're using the same 18 storms that we had previously, and we've got a time output interval of 2 minutes. We're running on the shortest time step to give the best chance of the model being stable, and we're going to hit go now. I'm going to foreshorten. It takes 2 or 3 minutes to run this simulation, so I'm going to pause the recording while it simulates. So the simulation is finished now, and as soon as it finishes it launches this stormwater control summary, and at the moment we're just looking at the 15-minute summer storm, the first storm in the analysis. So the first thing to do is to switch to the critical storm. We may need to expand the dialog box. But we can see that, firstly, notice that there's different storms for the different structures. It's the 240-minute winter for the 2 Suds features and the 960-minute for the pond. That's not unsurprising. But the main thing to notice is that because we are now storing water in the Suds structures upstream, the pond is now 36% over-designed. We'll deal with that in a bit, but regarding the 2 Suds features, the swale is just 3% bigger than it needs to be, so we could optimize that a little bit more. We could reduce the pass forward from the swale marginally to try and optimize that, but realistically we've done all we need to on that. The cellular storage is 8% over designed, so it is probably worth optimizing that a little bit further, and then we can address, only once we've got those 2 optimized can we address the over design on the pond. So what we're going to do is save the model, and we're going to create another new phase called optimized Suds design. So we've got our initial estimates there, so copy that, duplicate that phase and call it, rename it to optimized Suds design. That's the one that we're currently working on. You can see on the drop down there. So we're going to both switch off and stop analyzing the Suds design. We're essentially finished with that now. So let's see if we can get the cellular storage right first. It was 9 litres a second and 8% over designed. So I have to sort of give away, show you behind the curtain a little bit. I would probably have guessed 8 litres a second and run it. That was still a little bit over designed, so I then went to 7 litres a second. So let's jump straight to 7 litres a second. So rather than design flow being 9, we're going to go for 7. OK that. OK. Save the model. And again, we are going to analyze, and again, I'm going to foreshorten the time that it takes. Just going to cut out the 2 minutes or so that it takes to run the analysis. So the simulation's finished now. Again, we look at the critical storms. Those are the only ones we're interested in. Expand this dialog. We can see that the swale and the cellular storage are now optimized. They have just 3 and 2% storage available, so we can't do anything better with those really. That's fantastic. They're now optimized, and it's caused the pond to now be 40% over designed. So we can now reduce the size of the pond. So let's have a look what size it is, remind ourselves. So currently we've got 795 meters cubed, and this would be purely a process of trial and error. We would guess a size, simulate it, see if it was over or undersized. Either there would be a percentage available or there would be flooding, and we would increase or decrease the size accordingly. What tends to happen though is that we may think, okay, we're at 795 now, we're 40% over, so I'm just going to multiply that value by 0.6, and that's going to be my guess. What happens though is that once we make the pond smaller, it fills up, and it fills up more rapidly as well. Therefore, the water depth in the pond increases, and therefore we get more discharge out through the orifice and down to the outfall. So actually, although it's currently telling us it's about 40% over designed, it's actually a bit more than that. So you can be a bit more sort of aggressive with your guesses, if you like. That'll get you there faster, and it doesn't matter if you under design it, you just run it again. But the main sort of advice here is that a good guess is more than the 40% that's been estimated here. So again, I'm sort of cutting out a lot of the iteration that I went through. It took me 2 or 3 guesses to get there, but the way we do it is go into the sizing calculator, and this time we're going to set the volume to be 400, and then press OK on that. You can see it gets smaller. I think you saw it reduce there. Press OK, and we should see the size of the pond get substantially smaller. Just one bit of advice on this is, once a pond gets smaller, it can mean that the connections now fall outside of the boundary. So it's a good idea, I should have done this before I reduced the size, but it's a good idea just to move them closer into the center. It doesn't change the dimensions because we're using these no delay connections. It doesn't matter the length of these connections, but if you were using a pipe, you would want to check that the length of the pipe was realistic. It should go from the edge of the pond to the manhole that it's connected to. Okay, but the important thing is that they should all lie within the boundary of the pond, and if you're in any doubt about whether they're connected up or not, then you should use a flow path to make sure that you do have those connections. I think I already have one, so I'll check. Is it that one? Drag out flow path 1. No, that's down there, and that's down to the swale. So let's just do one final check, make sure it is all connected up. So I'm going to go right from the top to right to the bottom, and the crucial thing is that yes, I can see it's connected up. I can also do the show profile to make sure that we've got the swale and then through the pond and out. So once more, save. Once more, under analysis, validate. Yep, all good. And then run the simulation, and again foreshorten the time that it takes. I'm going to pause the video. Okay, so the simulation's finished now. One more time, press the critical storm, and we can see that there is just 2% available. And as I say, in reality, it may take you maybe 3 or 4 guesses to get there, upsizing and downsizing as you go along. But now all 3 of our structures are optimized such that they will all be just full but not over full during our design storms. And that's it. One last task is to resave the model.